Okay, so before I start today's class, and the one thing is somebody asked regarding the deadline for the assignment. So that will be 6th June. Okay, 6th June will be this Thursday. So by 6th June you submit. Okay. I will not be posting anything else, any other extension or something, but you can take this. Yeah, somebody said something. Yeah, you can definitely resubmit. Yes. So that is fine. And anybody else? Do you have any other question or anything else? Any queries? Okay, so we'll start from the filters as usual. We'll take a very quick recap. Okay, so that you don't forget. We have to continue from yesterday's. So as I told you, for microwave filter design, we start from normal lumped element uh, filters or lumped element networks, and that is how we generally do the analysis, right? ABCD parameter analysis, and then we extend this to our microwave domain. So that is done through particularly two different parameters. One is the image impedance or ZI, which can be linked to the characteristic impedance or the load or source impedance, and the other one is propagation constant or gamma. Okay. So from that gamma, you generally get alpha and beta. That means attenuation and phase shift parameter, which is actually linked to in the filtered domain, which is actually linked to start stop band and pass band. Okay. So that's why these two parameters, image impedance and propagation constant, these are very vital. But if you see all filter theory, the analysis is done at the network level itself. So initially we saw the the uh, how image impedance and characteristic impedance as well as the gamma parameter effects, how they are linked to each other. Then we saw a very simple network like T type network and pi type network. So what is there, Zi and gamma, and then we extended this to a very simple low pass filter which has L and C. Okay, and for this L and C type network, we calculated the alpha beta, which leads to the stop band and pass band. So this one was the constant K type filter, and then we said that we need some modification to have a better roll off, which is nothing but this M derived filter section. And then there was another problem that because of M-derived filter section has the another good has a extra pole, but after the pole the frequency or the response was falling off. So we need to cascade both M-derived as well as constant K to have a good response throughout. And then we saw like how to have a synthesis, right? Because we can just do analysis, but how to select the lumped components or then later the microwave components for a particular type of design. So generally what do will be what will be specifically mentioned for in a problem, design problem. So it's like how much attenuation is required in the stop band, how much ripple can be tolerated in the pass band, and the cutoff frequency. So mostly these will be the parameters mentioned, right? So there, the main thing we have to first select is generally the order of filter, that is N, capital N. So now how to do that? So for that, the books, in the Poser book you can go and or any other book, filter book. So they will give you a chart or a table. show you where they gave, even some cases in the project only, I found a plot for different types from n to at least like up to 20 orders, 20 different orders. They show the roll up. So you have to select which roll up is suitable for your design. So accordingly, you have to select first the order of filter. Now that you know the order, what can you do? So there are multiple choices, multiple different prototypes for filter. So like, Butterworth filter, which has a very, smooth or flat design in the flat, what do you call, flat response in the pass band, but it does not have a good roll up, right? So that is one option. But there are other options, right? Like, Chebyshev filter or elliptical filter or even Bessel filter, which will have ripples in the passband, but will give you a very good or very sharp um, roll up. So then you have to make a trade-off which one you want. So sometimes I saw in this book itself, Pujar book itself, they gave two different options. One is for 0.5 dB ripple in the passband, and another is 3 dB ripple in the passband. So you can take any one of them, and they gave two different tables with values of G. So what are these parameters? So coming to that, so all these different type of filters has a particular function which they follow to generate the lambda elements. So in this case, you see the Butterworth filter has a particular type of function to the power n order, and you have similarly for Chebyshev and elliptical and others. So the thing is, people have already done this analysis, and so to have a particular order of like n order Butterworth filter or Chebyshev order, what should be the lambda element required? So these they generally give in as a table. So directly you can find the table and use for your design. But the main thing is what you have to always remember that all these values are normalized. So this G1, G2 are not actually actually value of capacitor or inductor. So it is normalized. So your task is to find normalize. So get rid of this normalization and directly find the value of L and C, capacitor inductor, so that you can use in your design. So first you have to select the order and then you find out the values. Okay. So yeah, that is there. And then this, how do you remove the normalization? So that is what is done here. So there are two things here. One is the source resistance and another thing is cutoff frequency or omega c. So both has been taken as one. So I think yesterday somebody asked at the end that the values or the units does not match. So yeah, that is right, because the values like LK and CK, which is actually normalized in terms of with omega C and RO, are capital resistance. So generally, while doing the calculation, they have taken as a source resistance 1 and cutoff frequency of 1. So that is why when you need, let's say, you have to design a frequency, cutoff frequency of 4 gigahertz. So you have to, for calculation of your L and C parameters, you have to divide these things here as you see this, at the rightmost and the right and bottommost equation pairs. There it shows how to calculate L and C. L prime and C prime. LK and CK is given in the table. And now based on your RO and omega C requirement, you can select them. So now we'll go to the next section. So before, starting this, do you have any question until now? Mm. Okay. So after the quick recap, so we'll see like how to replace these lumped elements with microstrip line designs. Okay. So why there is a problem? As I told you before, the inductors and capacitors, like what you get generally in normal circuits, L and C values, you cannot directly put, right? Because they will come with parasitics. So the obviously the normal thing is the every lambda element comes with leads, right? Through which you will solder it to the circuit. So they itself becomes like a transmission line in high frequency. So that changes the value, and there will come the the packaging and all other things. All of them leads to a different value. That's why you cannot use lambda elements there. You have to use a equivalent section of microstrip line. And not only that, here if you see in this picture, let's say this is a low pass filter we have to replace with a, we have to design the same thing on a substrate. So now on the substrate, you cannot directly connect it. You need two pads, right? Two pads to connect L and C. Let's say you use lambda element only, you don't go to anything else. But how do you connect them? You need multiple pads to connect to your circuit, your on your substrate. Now, the moment you add these pads, they will lead to some extra additional impedances. So that will definitely change your line characteristics. Okay. So yeah, here I have one question. Why do you need a pad for lambda element connection in your circuit on your microstrip circuit? Why is a pad required?
The size of the lumped component may not be the same as the width of the transmission line.
No, that is not the case. See, generally it will come like as normal resistance and capacitance. It will come with a lead, right? Metallic wire or something that you can solder. So yeah,
But
my
we
point
need
is,
to take
yeah.
those things into our simulation so that we get the proper results when we fabricate it.
Yes, that is one reason. But without that, can you just put the lambda element on a substrate? Can you solder it?
No,
Why not?
There is also a solder mask placed on top of that, so leaving that reason, so that won't take the solder. So pads are placed so that post the design of the board, we can do the placement of the elements.
Exactly. So the thing is, here the hardware aspects come. Okay. So the some of you who has actually worked with a hardware or PCB hardware actually, so you will know on top of substrate, you cannot actually solder these components unless you have a metallic pad or metal. If you have microstrip line already present, on top of that you can solder. But where you have only substrate, no metal presence, you cannot solder a component there. So you can say like, okay, I will put some the metal there, the soldering elements there, and then put it. No, it will not hold, or it will only hold where metal already exists. So that's why the pad is very vital for microstrip line design or any lumped element, lumped component you have to put. Every time you have to use a pad there. Okay. Unless there is already a microstrip line existing in your circuit just next to your lumped element, in that case you are safe. Otherwise, you have to put extra pad. Okay, so now coming back to this. So Uh, definitely we can understand there is a lot of problems with using inductors and capacitors, right? So uh, this will be like some cases we can use. That will be the last resort. When we don't have any other option, then only we can use. But where is the first option? Yeah. So that is where it comes Richards transformation or commensurate line theory. Okay. So what does Richards transformation say? It says that you can replace a capacitor and inductor, lumped capacitor inductor, with a microstrip line section. either open circuit or short circuit. So this is like, very interesting theory and like very simple also, but it is like kind of the backbone of many microstrip line circuit design. This was done, I guess, around 1942. Richards, in his theory, he was a engineer in somewhere in USA during the Second World War. There, he proposed this theory. Okay, so if you actually think about this, is very simple. Normally, if you what you get from a transmission line circuit, the input impedance will be given by, if you take some particular length, you will have relating to J Z0 tan beta L. So Z0 is the characteristic impedance of the line and tan beta L is the electrical length and tan of that. Okay. So there is no omega function there. If you take the input impedance of a particular microstrip line section, it will be related to characteristic impedance Z0 and tan beta L. But normal capacitor inductor, you know that generally it is replaced. The impedance is written as j omega L or j1 by j omega C, right? So the omega function comes there. In this Richards transformation, what it says that this omega in normal circuit theory is actually equivalent to tan beta L in transmission line theory. That is actually equal. That is what you get here. The main equation is omega equals tan beta L. And this tan beta L you can actually replace in the equation of JXL. XL is the impedance for a inductor, which is J omega L. And this omega you replace with tan beta L and L. Then you get J capital omega L. And similarly, JBC. BC is the, is the admittance you get for a capacitance, or it is also called susceptance. So that is J omega C, which is nothing but JC tan beta L. And finally, you get both of them, J capital omega L and J capital omega C. Okay. And now if you take actually a lambda line of L equals lambda by 8, lambda by 8 means tan beta L will become tan of pi by 4 or tan 45 degree. Then it becomes 1. So then actually it gives the right hand side becomes capital L and capital C for both the cases. So that means if you take a line length of lambda by 8, okay, which is short circuited, then the characteristic impedance become of length L. Sorry, not length, is the value of inductance L. Then you get a value, input impedance of that line is capital L or inductor. Similarly, if you take a open circuit stub of length lambda by 8, which has a characteristic impedance of 1 by C. So that will lead to a input impedance, or that will be a equivalent capacitor. Okay, so there is two things. One is a short circuit stub of lambda by 8, which has a characteristic impedance L, will be equivalent to a inductor L. And similarly, the open circuit stub will be equivalent of capacitor C. Okay, so that is how you can make a capacitor inductor out of a open circuited and short circuited stub of length lambda by 8. And why is called commensurate line? While you follow this, all of the lines should be having a same length of lambda by 8. So that's why it's called commensurate lines theory. So this will be.
Here I have a question.
Yeah, sure.
What will be the inductance value? Can you get little large value for filtering, or it is as good as a physical inductor?
Yes, whatever you need, whatever you need in your microwave design. Okay, so that L you have to put. Okay, that should be, you have to remember that the characteristic impedance of the line should be L. The Z0 is getting replaced here by L. Okay, now there will be the constraints, like how less or how far can you go. That will depend on your microstrip line design. So you cannot make a very infinitesimal thin line, right? You have a design constant there. Let's say you have the minimum line width you can make, let's say is 0.5 millimeter. So that is the constant you have. So how high or how low L and C you can make, that will depend on generally the circuit design or the uh, hardware perspectives.
So
Yeah,
in the
any
circuit will
yes.
start dissipating also power.
Dissipating means no, because it's L and C, right? Ideally, it will be a lossless line, and L and C definitely it does not lead to loss, right?
Okay.
Yeah. Anybody else? Any question? This is very important, and you will need it in all microstrip line implementation. Anybody else?
So
Any?
basically
Yeah.
it will act as a filter.
No, filter we are coming later. This is simple,
Okay.
how you can implement a inductor and capacitor using a microstrip line. Yeah.
Okay.
Uh, One doubt, like you said, like the characteristic impedance of the line will
Hmm.
be equivalent to inductor value. It's like we have to choose
Yes.
such that.
Hmm.
Okay. But actually, normally, like if we see, like inductor will have reactance J omega L, as you said.
Yes.
So, like the characteristic impedance is like a impedance we will be having. So
Hmm.
we have to take only the value of inductor, like whatever we require the inductor value. Numerically, the value itself we have to see, or like with respect to J omega, I mean, like we have to even consider omega into L also.
Yeah. Actually, it will be normalized with omega L. Yes, it will right. It will be omega into L. So let's say you need to make a 12 picofarad capacitor. Okay, and that will
Okay.
be let's say some 5 gigahertz or something. Okay, so you have to
Okay.
multiply both of them, omega into C, and then you
Mhm.
have to find out what is the characteristic impedance. Yes,
Of
right.
the line.
So yeah,
Okay.
right. Yeah, here this
Understood.
normalization part is not mentioned, but you have to
Okay.
actually yes multiply with the frequency to get the impedance.
Yeah, that is clear.
Hmm.
And the main part, like what you like derived for this, like the omega is tan beta L.
Hmm.
So that is like you have used normal this the waveguide parameters and all, and you have finally arrived at this expression, right?
No,
As
no,
I
no, no.
actually see.
I have not arrived at it. The Richards
Okay.
transformation has arrived in this. The
This
basis
thing we
of
can find in Poser.
yes, definitely yes.
Okay, fine.
Everything whatever
I'll
I am following, you can follow in Pojer. Yes.
sure. I'll check once. Yeah.
Yeah, sure. This
Thank
is the backbone. This is what Richard said.
you.
He
Okay.
proved. Yes, rather I should not say said. Yeah.
Okay. Got it. Yeah.
Uh,
Thank you.
yeah. Okay.
I have one
Okay.
more question.
Yeah. Yes.
Whether self-resonant frequency will come into picture based on the component, no, with certain frequency it acts as an inductor. After that, it becomes a capacitance.
See, all these effects will come obviously, but those are non-ideal effects. So initially, first we will take the ideal things, okay, ideal components, and then we will, go towards that lossy component and all this. But ideally, it behaves very
Okay.
well. Yeah, you can actually make a short circuit and open circuit in ADS and design it, and you will see that it behaves like a capacitor inductor. You will get input impedance similar to a capacitor inductor. So unless you go to very high frequencies like millimeter wave and all, so normal frequency band, microwave band, it works very well. Okay. So next we'll go. Let's say now we know how to modify this or how to replace the lambda elements with transmission line section. Now we have to make the filter, right? So how do we do that? What are the problems there now? So yeah, this you have seen already. The normal L is replaced with the short circuited section, and the capacitor is replaced with a open circuited circuit. Okay. Now let's say in the problem is in a low pass filter, We have a inductor connected in series, right? So we have a inductor in the series arm. But this kind of microstrip line section, a stub of lambda by 8, can you connect in a series line? Is it possible? So in this, the schematic here, you need to replace this L here with a series stub like this, lambda by 8. How are you going to do that? Is it possible? You tell me that. Now, yeah, that is what I am asking you. So do you think is it possible to connect in series? Just insert in place of L. Can you put this short circuit section, lambda by 8 section?
Oh.
Yes.
Maybe I don't know why.
Yes, I think it
A
should be
crazy thought.
possible.
See, in the PCB, when you start fabricating between two layers, you just forms as a capacitance.
Yeah, right. But that capacitor is already part of microstrip line. It's not any extra thing you are bringing. If you have to add additional, you need to have a additional microstrip line.
Open
So
circuit divider.
my question is, see, just now we understood that the L and C can be replaced with a short circuit or open circuit stub. But now my point is, can you just put this, replace this here in this circuit instead of L? Can you put it in series here?
No, it's difficult because we have to short it with the like the ground of the
Yeah,
PCB.
yeah. It's not
So
only difficult, it's not possible only.
yes,
See, because if you see here, in the schematic, there is two lines. One is for normal power flowing line and the other one is for ground. So it will not be in series unless you connect the ground to the top layer. So that is not possible, right? You cannot connect directly to or short the ground to the top layer. So that is why you cannot connect a stub in series. In any microwave circuit line design, you cannot put an extra stub in series. So that is why we are our hands are tied. We can use here a series stub though. Here you see the capacitor we can easily replace. Okay, because the ground you can put or open circuit you can put, but the series one we cannot do. So what is the solution there? So that is addressed by something called Kuroda identities. Okay, so this is very interesting identity. So that is, I think the scientist Kuroda, he is also, this work is also quite very old, like maybe half a century ago or something. So what it says, you can replace the series stubs with shunt stubs some way. You can make it extra circuitry there, additional elements you can add to replace the series stub with the shunt stub. Okay. Now you see here. So it gives, you can replace, it gives uh, four different designs, but you can replace capacitor with an inductor, inductor with a capacitor, all these things. But it is actually very simple. Here in the first one, you see, it says if you have a parallel capacitor connected with a microstrip line section of Z1, you can replace that, which is equivalent to the right section picture on the right side, which is first you take a microstrip line section of Z2 by N square. The N is given by ratio of Z2 by Z1, and then you can replace with a series inductor. Okay, so left and right side pictures are actually equivalent. This is called a Kuroda identity. Identity because the left and right are identical. And the picture you see, microstrip line implementation, you see here. First section was capacitor is done through what? Open circuit, followed by a microstrip line section of Z1, which is replaced by first microstrip line section of Z2 by N square, and then a short circuited stub of Z1 by N square. So another thing you should notice that all of the line sections are of length L already. All of them are of length L. Okay. So length does not change. Only the the microstrip line section, the characteristic impedance changes. So if that changes, how will it affect our design? As you know, if we know the characteristic impedance, we can actually calculate through the line cal tool or any tool what should be the width of microstrip line. So that is how you can calculate and design a microstrip line. Now there are the proofs are all there in the, the how it has been analyzed and all the proofs has been given in the book. You can look into. But the interesting thing is it gives these four identities. Okay, where the capacitor in shunt can be replaced with inductor in series and vice versa. There are all four options available, and most they are very much useful in our design. You have to most of the circuits you have to use one of them. Just by playing with the characteristic impedance of the line, you can replace the short circuit with the open circuit or vice versa. Okay. Now you remember we had a problem, right? That we cannot connect a series inductor. So what can we do now? Now you see the second one. L is connected in series, right? Now here using this right hand side identity, we can replace that with a capacitor in shunt, which is normalized by C by N. This N parameters is calculated as 1 plus Z2 by Z1. You see, yeah, these are like very useful identities. And that is how you have to actually analyze your or you have to design your circuit. You will know some L and C values, and then you have to replace them with this. So yeah, do you have any question here? Is it clear? So is the Kuroda identity clear?
Yes, yes, yeah.
Oh, okay, okay. And these will be even more clear when you actually do the next design assignment. Okay. So in theory, it looks like okay something or something unless you do yourself. So that it will be your next assignment. Okay. So now these are some examples what you get. So maximally flat or Butterworth is the left one, and you see a equiripple filter in the right side. So one you get for 0.5 dB ripple and another is 3 dB ripple. So you can clearly see how the roll-ups are different for the two different cases. Okay. And this one you see there are two plots and both of them shows a red and blue, right? Now this red one is implemented using Richards and Kuroda using actual microstrip line section. So there you see although it almost follows the blue circuit, but there is a problem that it actually repeats after some frequency. It is like periodic behavior, right? Why it happens? Because all the microstrip line sections are actually periodic response because tan beta L is there, and beta L is a frequency is a function of frequency. So that is why all these responses will be like kind of periodic. That is what you get. So that you should remember. Okay. So now that we have understood this portion, so now you have a way to implement the normal the low pass filter using this circuits. Okay. Now there is the question is there any other option available for low pass filter implementation? Yes. So the answer is there is a very simple way to implement. It's called stepped impedance filter, low pass filter. Stepped impedance. Okay. Stepped means we will take multiple sections of microstrip line which has a defined value of characteristic impedance. Now we'll see how it is designed. Okay, so the first one is if you see a ABCD matrix, which is for a microstrip line of section L of length L with characteristic impedance Z0 and phase shift beta. You will have a ABCD parameter of this cos beta L and just this like this. So this ABCD matrix, it is very useful, and I will advise all of you to calculate once. It takes 5 to 10 minutes, but you will understand a lot of things from this. And this is very useful for any RF circuit analysis. For a microstrip line in the left hand side, you should actually calculate yourself how this ABCD matrices can be derived. You should derive that. Now, let's say we use this ABCD matrix to actually implement a T network like this, which is required for our normal L and C filter, right? Now, what happens? If you calculate for this network, you will get the Z2, the Z1 and Z2 values is equals to Z naught cosec beta L, and Z1 will be equals to Z naught tan beta L. I am saying if Z1, Z2 are replaced in microstrip line section, and then you calculate the Z matrix, you will actually find out what would be the value of Z1 and Z2 in terms of microstrip line. So it says it will be actually Z2 will be this and Z1 will be tan beta L. Okay. Now what are the implications of this? Yeah, implication is now the series arm, which one Z1 by 2 is written as X by 2, which is nothing but the inductor value. It can be written as Z naught tan beta L by 2. And similarly, the susceptance value or the capacitor value in the parallel arm can be written as 1 over Z naught sin beta L. All right. So now what is this? What can we get from these two expressions? Very simple. So for a short length and large Z naught, let's say Z naught value is very large. That means characteristic impedance is very large and the line length L is very less. So what will happen? The first case, X will become close to Z naught because tan beta L by 2 will become beta L by 2 and your value of X is equivalent, almost equal to Z naught beta L, and B becomes 0 because Z naught is very high and L is less. Then in that case, you can write XL as Z naught beta L. You can simply write the inductance as Z naught beta L for a very short length line with high characteristic impedance. Similarly, if you take a short length line with very small characteristic impedance, you can see you can just put here in this trigonometric equation, and X becomes 0 and the B is the reverse of 1 over C, is becomes Y naught beta L. So is the susceptance is close to Y naught beta L. So you can just replace a capacitor with a very small Z naught, very small characteristic impedance and short length line. So that is another equivalence. Is it clear? Is this part clear? How you can replace a capacitor inductor with a large and small characteristic impedance lines with very short length? Do you understand these two equations? How we are actually getting this capacitor inductor values?
So it means like for a capacitance, we have to make very short length and a wide trace in microstrip. So
No,
we
no,
can
no.
realize the capacitance. Correct, no?
Yes, right, yes, right. Yeah, so that's why you see in the picture, you see in the bottom picture. So actually this low pass filter will look like this. First, there will be a Z naught line, normal microstrip line. Then you have a large Z naught. So large Z naught generally has a very thin line with
thin.
so that is what L is with replaced by a thin line, and the capacitor is replaced with a very thick line, that is small Z naught, and then you have cascade of multiple sections like this.
Okay, but in this case, we have not used any that CODAS identities or something. Like normally, like this is a different approach again.
This
Like
is a different
for a
approach.
simple,
Yeah, right. Yes.
because here also we are seeing a series inductor, but I think we are just following this approach and replacing it with a
Uh,
thinner microstrip line
yeah,
with a short.
you are right. Yes. This is a
Ah,
different approach. This is actually, if you see that, the fabrication will be much easier, right,
yeah,
compared to the other one. Yes.
correct.
Yeah, but there are some problems, there are some limitations, right? Because these lines you cannot make, indefinitely high, thicker, and the thinner
Mhm.
lines you cannot make as thin as you want, right? So
Correct,
there will
correct.
be
Some
some
limitation
limitation there. Yes.
with respect to the manufacturing.
Manufacturing, yes, correct. So generally, you see here it is written, the impedances are fixed by fabrication limits. So generally,
Okay,
you
okay,
can go
got
up
it.
to 5 to 200 ohm characteristic impedance. You can as low as 5 ohm and go as high as 200 ohm. Okay.
Mm.
So that is how you have to see the design perspectives.
It also depends on the fabrication capability mainly.
Yeah, right. Yes. So this will be one in one of your um, assignments, next
Mhm.
assignment. So you understand this, and also I will look. This is the simplest filter design possible and very easy to fabricate also. I will suggest that you read this carefully and even look into the book also. It is just 2-3 pages, so you'll understand very clearly. So the good thing in Fuzzer is that there will be many different approaches possible in for filter design. They will give a uh, solved example for each one of them. They will give some parameters and they will solve the parameters and actually show how to get the design parameters. Okay.
Oh,
So
okay.
those examples you can see.
Yes, sure, sure.
Okay, so this is actually some simulations of this using the previous stepped impedance filters. So you see, even though it works very good in the pass band, but there are some problems in the stop band. You see, the periodic response is always there. So that is one of the challenging things in microstrip design. Okay. And now, so far we have seen only low pass filter, right? So if you have to design a high pass filter, what do you do? Actually, it is quite easy, it seems. If you know all the parameters for a low pass, you can, it says, the theory says, you can just replace the frequency with reverse of omega c by omega. Okay. That means if you put there, your inductor and capacitor values will actually interchange. So from the previous, how you are previously calculating, so there the capacitor inductors will actually replace each other with some changes in the value as it calculated here in this two equation, Ck prime and Lk prime. Okay, you see Ck prime is related to here now in Lk. Okay. Previously your Lk was in low pass filter, Lk prime was related to Lk, but now here Ck prime is related to Lk. Okay. So if you to design a high pass filter, you have to think in a way of low pass filter only. Okay. So you have to again go back to the tables, either Butterworth or elliptical or Chebyshev. You have to select the order and then you have to do this frequency transformation. You have to use this omega by omega c, this equations you have to use. You can just use MATLAB or any other tool to calculate this CK naught and LK naught values. And using this, you can as usual follow the filter design. You can follow Kuroda identities or any other designs to calculate your filter, high pass filter as well. Now, next question is even very important is band pass or band stop. Again, it comes back to the same point. Everywhere, it's like what is very useful is that the people who have the scientists or professors, whoever has worked in this field, they have generalized the design. Okay, they have generalized everything in terms of low pass filter. The tables, whatever is already available, given. Now you can use the same tables for even high pass filter design, band pass, band stop, everything. Just you have to use a defined transfer function. Okay. So similarly here, if you are given, you have to design, let's say 4 gigahertz band pass filter, which center frequency is 4 gigahertz, and let's say your bandwidth is 10%. Okay. So from this 10% bandwidth, you can calculate what will be the omega 1 and omega 2. That is nothing but the lower cutoff and higher cutoff for a band pass filter. So using that, you can calculate just this, omega, del value, and using this omega 1, omega 2, all this calculation, you can calculate the revised xk and dk inductor and susceptance value, inductance and susceptance. So for that, as usual, the LK and CK you get from the table, and you have to normalize them with del omega naught and omega, all these functions. Okay. Once you get these parameters like xk and bk, there the term your work starts. How you actually implement with microwave microstrip line. But you can, so far you can do the design in any some circuit or lumped element, anything. But microstrip line design is another challenge that we will see. So actually, if you see the inductor, if you follow the previous one here, what we are having a normal inductor LK. If you put this replacement or this 1 over delta function here, omega minus omega naught function inside parenthesis, if you multiply with LK, what you actually get is a joint LK and CK term, right? That means for a bandpass implementation, what you need is a series capacitor inductor together, which is called a resonator or a tank circuit. If you have read the normal network theory, you will know a series and a joint L and C together, they leads to a resonance. Okay. That's why they are called resonator or tank circuit. Now we'll see how they are very important for band pass or band stop filter design. Okay. These tank circuits or resonators are very important. So that is what it shows here. See, normal L actually changes to a series L and C. And a parallel capacitor is actually replaced by another parallel tank circuit. So now we'll move on to see some of the bandpass filter design. Okay. So although, what I will tell you this, filter design or bandpass filter design itself is quite involved. Okay. It takes a lot of efforts to do a bandpass filter design, especially. High pass and low pass are quite okay to design in even in microwave. But if you need micro bandpass filter design, it needs very in-depth effort. Okay. That no, I cannot cover that much. It might need a separate course itself. I'll give you one or two types. Okay. But if you are more interested, the poser is there definitely. And even more, even in the poser book also, most of the pictures, if you see, this is the poser book I have opened here. So this pictures are taken from another book. Okay. This is this book. I will suggest, if some of you are very interested in filter design itself, I will suggest you go to this book. It's from Mathey, Young and Jones. It's quite old book, but still now it is kind of like backbone of filter design. Okay, this book deals very in depth. I have not seen any that kind of design in any other book yet. Okay, you can look into this book. Who among you who are looking for only filter design or something, you can look into this. I will cover one or two topics in bandpass filter design. So yeah, here in this picture you see one of the simplest ways, at least in the fabrication wise simple, is having a capacitively coupled microstrip line, or it's also called capacitively coupled resonator. Resonator is, we'll see how, as I told you, this resonator concept is very important in bandpass filter design. These line lengths of characteristic impedance Z naught will actually act like a resonator. And if you actually stack all of them or cascade multiple of them, then it will look like this. You know, the second picture in the middle, it actually shows a microstrip line circuit implementation. It will actually look like this: coupled line, microstrip line section. So in this picture, there are three different designs. Okay, first one is capacitively coupled and series microstrip line. Second one is coupled line microstrip line implementation, and third one is shorted line. Shorted means they have shunt stubs in shunt. So in all of the cases, you have to first calculate L and C values, and then you have to translate to the bandpass filter. But in all of them requires very elaborate analysis. Okay, we'll see now we'll see a few. Okay, we will modify this. This will be your kind of almost similar filter homework you will get. Okay, assignment for next filter. We'll post it. I will post it. Maybe a couple of days later. Okay, so before moving to this, I will take a 5 minutes break and then come back. Okay? I'll take a 5 minutes break before this. Okay, so I am back. So do you have any questions so far? So yeah, otherwise we'll start the resonator side. Just a minute. Yeah, actually, yeah, it's raining so much in Bangalore here right now. The rain is even entering my room. Okay. Okay. So, mm, okay. So the basic types of resonators are series RLC and parallel RLC, right? These are the resonators you must know about in your normal lambda element circuits, right? So if you actually calculate the Z in, it will come as two defined terms, R plus j omega L and 1 over j omega C. It's like very simple things. And you can actually, relate the microstrip line resonator to this kind of resonator. That is where we are actually going in that direction. And we'll see, see why these are related. And generally, the resonant modes, or also called IGN modes, they are linked to the geometry of the device or circuit, all this, okay? And if the frequency will be, or the characteristic modes will depend on the structure. Now, if we actually calculate the Z in for this kind of circuit, and because it has a resistance connected, which is R, so that's why it's called a lossy resonator. Okay. So in the series case, you see, if you calculate, it comes like R plus J2L del omega. In the shunt resonance case, you have R over 1 plus J2. So the expressions are almost like, inverse. So now the question is why suddenly we are interested in resonance? Because if you see the plot of a resonance circuit impedance, it actually looks like either band stop or band pass. See, yeah, if you notice, it looks like a band pass or band stop, right? This impedance, just a Z in what we have calculated for series and shunt. You see, in the series case, it has a dip. It goes to minimum value in the omega equals omega naught. And in the other case, it actually becomes maximum in the when omega equals omega naught. And there's another very simple way to approximate a lossy resonator with a lossless resonator is using this transformation. Omega naught is replaced by omega naught plus 1 over J2Q. Okay. The Q is the Q factor for the lossy one. That means a lossless resonator, you use the same expression and just replace the omega naught by this. You will have a uh, lossy resonator also, the same expression. Okay. Because if you actually calculate for lossy or take the resistance everywhere, the calculations becomes very complex. Okay. So you can do for a lossless and then replace the omega naught value with this. The calculation becomes quite easier. And as you see, so the impact is the resonance frequency changes because of the loss part. Okay. Now comes to the transmission line section. Can we use a transmission line section to create a resonator? Instead of this RLC circuit, what can you do with the transmission line now? Now it says, if you take a lossy transmission line, the input impedance is this, this expression. This is comes from the normal transmission line theory. If you calculate, if you take a length of L equals lambda by 2, then you calculate and put all these things there. Ultimately, it simples down to Zin equals Z0 by this function, which is actually, if you see, is equivalent to a parallel resonant circuit. So what we are saying is now, if we take a microstrip line section of length lambda by 2, which is open circuited, okay? So it is lossy or lossless, let's say. Both are okay. But the main characteristics is length is lambda by 2 and open circuit. Then it behaves like a parallel resonant circuit. And then you can actually calculate RCL values and Q equivalent values. When it becomes lossless, obviously alpha becomes 0. Then it comes to simple J naught cot beta L. Okay. So that means it says a microstrip line, open microstrip line of length lambda by 2 behaves like a resonant section. So we can use a lambda by 2 microstrip line section. We'll use them to actually implement a band pass filter. That is what comes next. So one of the important implementations is called gap coupled resonator. What is that? It is this one. So the first one here you see is called gap coupled resonator. The gap means between two microstrip line section there is a air gap. And the successive transmission line sections are of length lambda by 2. Okay, they are of length lambda by 2 and they are open circuit in the other end because of the gap. That's why it behaves like a resonator. And this complete implementation is called a gap coupled resonator bandpass filter. Okay, that is what we are talking about, the first one. Now, how to analyze this? So if you want to analyze the section of that, okay, which is like this, okay, you have a feed line, you have a gap which is replaced by equivalent capacitor, and you have a length Z lambda by 2 microstrip line section. So you have to basically calculate the first, the Z, the input impedance looking at the other section. That it comes like, if you take as like this, is simply the 1 over omega C for the capacitor and the line section together. If you just add them in series, you get a function like this. Okay, J tan beta L plus all this, something in the series and something in something in numerator and some other term in the denominator. Now, as you know, for calculating resonance, what do we need? We have to get Z, the impedance value Z of this should be 0. How can it be 0? Only when the numerator terms become 0. That is why we get this equation. Tan beta L plus BC equals 0. Now, as you know, you might know that not all of the equations you can solve through math. Okay. So especially this exponential equations and some of these tangential trigonometry equations which cannot be directly solved is called transcendental equation. Okay. These are generally solved numerically or through graphical solution. That is what is done here. If you have to do this, solve this where this tan beta L plus BC becomes 0, we simply plot tan beta L and BC. BC is the value here, 1 Z naught omega C separately. And then where both of them becomes equal value, and minus, then obviously the together they will become 0. So you understand, right? This graphical approach. We plot both of them separately, and then where these plots intersect, this these values actually says where the resonances will occur. So as you see here, the tan beta and this BC plot actually intersects close to pi. The first resonance happens close to the x-axis is beta L, which is related to frequency. So first one happens close to pi. And now as you see, actually because of the coupling, the omega is actually lower than the pi. Okay. So that's why this coupling or the air gap is actually reducing the resonance frequency, as you can see from this picture. Okay, so far, do you have any question on this section? I hope you guys are here. Okay.
Yes, yeah.
Okay. Okay. Okay, somebody said the screen stuck. No, the screen was not stuck. Okay. Okay. So coming back to this, we can implement the gap coupled microstrip line for a bandpass filter design. And the basic analysis comes from this. Okay. How you can take a lambda by 2 resonator line with a capacitive section. See, the important point you should note that why the capacitive line is required. Okay. I will note you. Yeah. If you see this lambda by section, if you can directly connect with the other transmission line, then it will no longer be a resonator. Why? The first one definitely because the length changes, and the second one you cannot give a open circuit on the other end. So both of them are actually addressed together by adding a capacitive gap there. See how ingenious this is. Just a simple gap to address that issue. So you keep a microstrip line resonator section as well as it behaves like a coupled line. Sorry, not the coupled line. Together it behaves like a resonator section. And the only the limitation is that because of adding the capacitive gap, the frequency is actually resonant frequency is reduces. That is only one limitation, but we can live with that. Okay, so now the analysis is done like this. So from this intersection of these two plots, we can calculate where the where the first resonance will happen. And if you actually, expand the value or the equation of z omega, so this is, it's called Taylor series in math. You can expand in terms of derivative of a function like this. And at omega 1, let's say omega 1 is the resonance frequency, right? So at obviously z at omega 1 becomes 0. Then you live with the first term. What it leaves us with the first term. And that if you actually simplify these equations, all this put, finally you get the value of impedance is 0 pi of this value, something in numerator and something in denominator. So now why we are all doing to show that actually all of these are actually equivalent to a parallel resonance circuit. Normal RLC parallel resonance circuit can be replaced with this. Okay, this structure. That is what we are trying to do, right? We are trying to do a bandpass filter using microstrip line. So now you see the expression what we got from last section is like this. Now if this is for a lossless. Now we told you, right, to substitute by this expression for a lossy one. So with this, if you do, it simply becomes like a section, additional section is added on top of this. So this is because it's as if like a resistance in the series. Now, as you see, first we started with a parallel resonant circuit. And because of the capacitive gap, what we get here is equivalent to a series RLC. So that means the function is getting inverted here. We started the normal lambda by 2 microstrip line gives the response of a parallel RLC. But when you add this capacitive gap and calculate the impedance, it behaves as if like a series RLC circuit. Okay. So that means this capacitive gap acts like an inverter, impedance inverter. So that you should remember. This is another important topic in RF circuits is called impedance or admittance inverter. That will come to next. Okay. But the main point is the lambda by 2 microstrip line section along with this gap you get a resonance series RLC circuit which behaves like a uh, behaves like a resonator circuit and will give you a band pass response. And you can actually calculate the coupling factor and all this for this. It's simple to is similar to normal resonators. So here is the gist. A lambda by 2 circuit will behave like a parallel RLC. Lambda by 2 short circuited transmission line will behave like a series RLC. And similarly, lambda by 4 lines will behave like a series or parallel RLC. And in all of these cases, if you add a gap coupling, it actually inverses the impedance. That's why it's called impedance inverter. Another impedance inverter is also called lambda by 4. Simple quarter wavelength line also inverts your impedance. So now if you see here, this is the theory for impedance inverters. So why it is used? Sometimes you want to use only series or only shunt elements in your circuit, in your microstrip filter, let's say. So as you saw in the stepped impedance filter, where all of them were connected in series, right? That simplifies the design. Similarly, this is another approach. Just like Kroder's identity, this impedance inverter is another approach to simplify your design. If you have a series, you can invert it. That will become like a shunt, and shunt will become inverted to series. If you use these inverters, so they are also called J and K inverter. So these J and K functions, you will see it is widely used in our microstrip network explanations. Okay, everywhere it is used. Many of the places. So you can see these are all taken from the Puzar. So on depth analysis, the simple implementation is just a lambda by 4 line. Okay. And otherwise, you can do like a capacitor in connected in between or inductor connected in between. That will also act like an inverter. So you see in the input side, Z in what you get for a load ZL is K square by ZL. That's why it's inverted. Okay. And similarly, the admittance side, you get J square by YL. Your load is YL, but what you see in the input side is inverted version of the admittance. So these are actually used in bandpass filter design. And what we saw in the last one is actually this. We have used a coupled line section, right? That is what this JB is. That is, we have used actually a admittance inverter. So now if you actually, cascade many of these sections, so then you can calculate the bandpass response, and you can actually get the parameters, design parameters through that. So for this, the equations are listed in the book. Okay. So you will have multiple equations, they are listed. You have to use that actually. Okay. But the basic analysis or the basic theory is this. Okay, so far so that topic ends there. Do you have any other question? Any question on this topic? The last topic today is the coupled line that I will touch on. We'll see like there are very variety of uses of coupled line in microwave circuit design. I'll just touch on that. Hmm. Yeah, any questions so far? Okay, okay. So yeah, so maybe just a minute. Okay, so the couple lines are nothing but two parallel microstrip line on a substrate. Okay, why they're coupled? Because obviously, if you keep two metallic strips together, the wave will be coupled between each one of them, right? So they will be having a capacitor in betweens and all this. So that's why they are called coupled. So these coupled lines are useful in many cases. Like, you can make hybrid directional coupler, and even in filter design also they can be used. So as you see, this simple couple line is the ground layer as usual. And on the top layer, instead of one microstrip line, you are putting two microstrip line with a gap. So that can be designed, or can be, the equivalent circuit can be written as a capacitance in between them, and there are two capacitance from top to ground through substrate. Right. Now you see, so generally the simple circuit analysis is done, as you know, in terms of even and odd mode analysis. So even mode analysis is you give same voltage to both of them. The bias should be the same, excitation is same voltage for both of the line, and then you get a odd mode characteristic impedance. So that is termed that ZOE, and Vp is the phase velocity for the odd mode. Sorry, this is the even mode. So even mode, phase velocity and impedance you get. Similarly, for the odd mode analysis, you bias one line to plus V and another one to minus V. So definitely at the middle, it becomes like a grounded. So it acts like electric wall. So for this, you can also calculate ZOO and VPO, phase velocity and characteristic impedance for the odd mode. Okay. And through that, then these things will be required for your design. So very in-depth analysis, line by line, is given in the Puzar book. So if you are interested in the derivation, you can look into. But the point is, if you follow all this expression and equations, all this, ultimately you get a very big table in Puzar book. Okay. So few of them are used here, which can be used for band pass or band stop filter. You see, just a simple coupled line where the two opposite ends on the other side are shunted, and the other two ends you can actually use for connect to your line. Then it behaves like a band pass. That is the first structure. You see, band pass is in the middle, around pi it passes. On the other two ends there is a null. It's like a zero. That's why it's a band pass. And the other case, when you have open circuit instead of short circuit, then it behaves like a band stop. And using this, not only band stop and band pass, using this multiple defined combinations of open and short, you can implement low pass, high pass, all defined filters you can actually implement. So I'll suggest.
Yeah, actually, the first
Hmm.
1 second, I have small doubt. The first one, when we short the lines, uh, it is a band pass response. Is it?
It is a band pass response. Yes, yes. Sort the lines in the top, upper
I
half as well as bottom half. Yes.
like even in the open case also we are seeing the band pass, but it's like both the things they're calling band pass, like the first row and the second row, that rightmost column.
Mm-hmm. Okay. Okay,
Because the
okay. Sorry,
responses are like
I
different,
thought
right?
I told band stop, right? Sorry. No, it is actually. Let me then confirm
It
from
should
the
be
book
downscaling.
itself. Yeah. Correct. There might be a change there. Let's see.
Okay.
Yeah, right. So, but yeah, it says actually band pass here in the book. See, this is the table from the book.
Mhm.
Actually, it says band pass. Yeah.
Okay. Mm,
But see, this is the plot of impedance, right? It's not the plot of the gamma or
okay,
the
okay.
alpha or
Filter
beta,
transfer
right?
function.
Yeah. So that you should remember. Yes. So if you actually
Okay.
plot that, that will give you
Mhm.
the characteristics.
Correct. Okay.
Mm. Okay, so these are so definitely you can use this and these expressions you have to use to design a band pass filter using this. And as you see this table, so this is band pass, low pass, and all stop. So these defined combinations are possible. Okay.
Mm.
So actually, the for band pass filter design, so generally they replace a simple um, coupled line with open circuit. Coupled line with open circuit. So they say that mathematically you can replace this with a impedance admittance converter J type and two microstrip line section of length theta at both sides. That is what they say. And many of the other bandpass filters you will see, this is the basic design for analysis. They all of them are generally analyzed in terms of a microstrip line section as well as a admittance or impedance converter. So then they start the analysis and show like how to get. Okay, but I will not go into that details. There is like very heavy maths and analysis has been done in the book. You can look into that if you are interested. But ultimately, you will get a structure like this. If you actually want to design a bandpass filter using this coupled line section, only one section obviously will not do, right? You have to go to nth order. So then you have to cascade all of them. Each of them will have a, you see the is expressed in terms of ZOE and ZOO. So each couple line will have two characteristics now. One with even mode impedance and another is correct odd mode impedance. Using those, you can calculate the line length, width, and all these things. And the line generally says, the approximately lambda by 2 length. And the gap between the line is a very crucial thing for this calculation. Okay, so these are all this, you can find in the book for design. So finally, you will have a, this red colored thing. This is the for calculation. You can calculate L1, L2 from the for your filter, and then you have to, get back the design parameters. Okay. So even if you see, even in the book also, they have not provided everything in this Pojar book. So they refer to that other book, if you remember, I showed you in the before. So which was like, yeah. So the first reference here, in even the Pojar, they refer to this book for filter design. So some of you who are very interested in filter design should actually look into this book. Okay.
So they are basically microstrip based filter design.
Yeah, basically microstrip line, coupled line, and all this. Yeah, basically microstrip. Yes. Yeah, but it's quite old book. You will not get in a very good PDF format or
Oh,
anything. Yeah, but still you can learn from this.
okay.
Yeah. Okay. So yeah, resonance circuit is nothing new. So yeah, this is so far today's thing, and I will show you finally. You see this Pojar book. This is very interesting. I found. They gave actually a filter prototype along the photograph they shows of a wideband down converter. Okay, so in that this might be old picture nowadays might be more compact and all, and they says it works for 10 megahertz to 27 gigahertz. You see how broadband frequency it covers. 10 megahertz till 27 gigahertz it covers. So definitely it requires lot of filters and all this, right? So it says, this can be seen in the module including stop filter what we saw, coupled line filter and stepped impedance filters. All the things has been used here. And the microstrip stub filter you see here. So lot of parallel stubs has been used here in this. This is the left side picture. Okay, and in this section you see there are a lot of coupled line filters and the stepped impedance filters all are used in this. So this is how the picture actually shows actually looks like. In between you see there are a lot of lines connected in cascaded. Those are the our filters. So, okay, so the filter theory ends here. And next week, I will show you some actually some design in ADS. And generally, I will not go into the band pass filter, low pass and high pass only I will show you. And then you will also have to do low and high pass. Okay. Because band pass filter requires more in-depth study. And if you are interested, you can do. But the homework will also be on low pass and high pass. Okay.
I have one doubt actually.
Yeah, sure, sure.
Sir, may I know the why while inductors some value will get no sir, like 11.2 nanohenry like that will get means
Sorry, it's not clear. Come again.
exact value cannot find no sir in
The if you have to use lambda
Mm,
element, right, yes.
like Henry it can the exact value we cannot find no sir.
No, yeah, that's why we
Exact
are
value or
yeah, that's why
exact
we are
value
doing.
of 11.2 we cannot find. How
Cannot-
can we do? How can we do then?
Yeah. So that is the design. That is what you see, right? So you have to first of all, we are not using. We are trying to avoid the lambda elements completely, right? We are trying to do by using microstrip line. So there you can do anything, whatever you want, as far as your fabrication supports. Yes.
Yes, sir. Yes, sir. We are using one module actually down conversion only. From 2 to 18 to we are down converting to 140 megahertz, 140 to 240 megahertz like that we are doing down converting.
Okay.
Okay, in that lumped filters also we are using, sir.
Okay.
Why may I know the reason? Reason may I know, sir?
Sorry, why? What?
Why we are using lumped filters also in that
Okay. See, yeah. Okay. See, only the lambda elements you have to use sometimes because, as I told you, no, there are limitations in fabrication. You can make everything in microstrip line, but many of them you cannot fabricate actually. Okay, it may not be possible to fabricate. So that's why then you have no other way, no other choice, just you have to use. But actually, if you use all this, theory, the Kuroda transformation and the this, then it might be you can find another way. That is what the design you have to work out.
I have another doubt. While we tuning that bandpass filter, if you want bandwidth shifting, you will use capacitors.
You are saying bandwidth, changing bandwidth.
Bandpass
Yes.
filter. Bandpass filter. If you want flatness, means we will do with inductors. What we round up, no? Yeah, I think you got what I'm saying.
I mean, not completely.
That one only we're tuning. That inductors only we're tuning.
Okay. What you are saying? Yes. Right. So yeah, ultimately we are trying to replace the L and C
in that
with this.
in that inductors only we will tune.
Right.
Yeah. Okay. While inductors only we are something we are making some
Yeah.
disturbance on the inductor only.
Right. Yeah, but if you see initially only we moved from L and C.
Perfect flatness.
Actually, if you see, we started from the theory on the resonator, right? Parallel resonator line. So we are trying to replace not the L and C anymore. We are trying to replace the resonator circuit now. Yeah, somebody asked a question.
Okay.
Yeah, tell me. Yeah.
Yeah.
Okay. Anybody else? Any question? Otherwise, I will stop it here.
Sir, I have a question from coupler itself. Last
Coupler
time that we
itself.
have seen.
Coupler. Yeah, sure,
Uh-huh.
sure.
So if I want to design directional coupler for the wideband, that is my frequency is gigahertz to 3 gigahertz. So should I go with the same theory, or I will have to search for another literature for that one?
You want to design wideband, you are saying?
Yes, yes,
Ah.
directional coupler. My frequency band is from 1 gigahertz to 3 gigahertz.
1 gigahertz to 3 gigahertz. That you can do generally using one only. Okay. Generally, normal rat race coupler will give you good bandwidth. 1 to 3 gigahertz, I suppose it might be fine. You can design for 2 gigahertz and then you can get it actually. Did you try with rat race coupler? Yes. Yeah, try with
No, sir, I haven't tried it yet. Okay.
Okay, so try it, and even with branch line coupler, you will get it. Yeah. And generally, see, if you a very simple way to get better bandwidth is just cascading multiple section. If one branch line section does not give you good, you can just use two.
But sir, when we cascade two couplers, so in between, should we have to compromise with respect to our parameters?
Yes. Something. No. Oh, okay, you are saying the design itself. Okay. So yeah, that you might have some things there. So you can look into some papers there. Okay. You might see. Generally, if the normal rat race or branch line coupler, they give very good bandwidth only. Okay.
Okay. Okay, sir. Okay, sir. Thank you, sir.
Okay. Okay then. So we'll stop it here today.
Sir,
Yeah.
Sir, I have one doubt that suppose if I want to design any circuit for a particular band, any frequency, then for deciding the width of that microstrip during our ADS, so like should we design at center frequency and calculate the line width using cal tool, or like what frequency should we target? Suppose if our requirement is wideband, then to calculate line width, which frequency should we target?
Generally, you should target the center frequency only.
Okay.
Yes.
Thank you.
Like I have one small doubt.
Yes.
The gap cover